Hey guys, Mr. B here. In this video, we're going to be going through the practice problems for Chapter 8, Section 4 on polarity. So let's begin here with number 1. It says, what type of bond, nonpolar covalent, polar covalent, or ionic, will form between each pair of atoms? All right, so to answer this question, what we're going to need to do is we're going to need to look at the chart given to us in the notes that gives us the electronegativity values for each element. Okay, so let's go back and take a look, and that's this chart given right here. And we might need to zoom in a little bit to see this a bit better. So for the first one, we have sodium, which is 0.9, and oxygen, which is 3.5. So let's go write that on our notes here. So 0.9 for sodium. I apologize, we're a little bit zoomed in here, but either way should be okay. So we have sodium, which is 0.9, and oxygen, which is 3.5. All right. So first thing is find those values. Okay. Second then is we need to know what's the difference between those values. So if we subtract these two, we're going to get a difference, and we have another chart here that we can use that will tell us if that difference falls within a certain range, that's what type of bond it will make. So if we take 0.9, and I'm just going to use my cell phone here to use my calculator. So you take 0.9 or 3.5 minus 0.9, we get a difference of 2.6, and that is greater than 2, therefore it will fall in the ionic range. Okay, so for this problem, our difference, there we go, our difference is 2.6, therefore this is going to be ionic. Okay, all right. Next one here, we have oxygen and oxygen. All right, so this one's going to be pretty simple because we have the same element, and therefore the difference is going to be 0, right, because it's the same element. So they both are 3.5, therefore the difference, I'm just going to write diff, okay, is equal to 0. And if it falls in the range of 0 for difference, let's go look back at our chart here, then it's going to be a nonpolar covalent bond. So this is going to be nonpolar covalent for letter B, number 1. Okay, so oxygen and oxygen, that will be nonpolar covalent. So we'll just say nonpolar. Nonpolar. All right. And the last one here is phosphorus and oxygen. Okay, so let's go look at our values. I don't know what phosphorus is off the top of my head. I do know that oxygen is 3.5 because we had that one in the previous examples, so 3.5. So let's go take a look at phosphorus and see what that value is. All right, so phosphorus is over here. So see, it looks like it has a value of 2.1. All right, so our phosphorus value is going to be 2.1. So 2.1. All right, so then let's take a look at the difference between these. So our difference, so we take 3.5 minus 2.1, we get a difference of 1.4. And in terms of where does that fall on our polarity range, let's take a look at our chart. And between 1 and 2 is considered very polar. All right, so we are going to consider this to be very polar. So let's click down here. Oh, I'm going to move this every single time, it looks like. A little bit annoying, but that's fine. So very polar. There we go. All right. So zoom back out here. Let's take a look at number 2. How do electronegativity values determine the charge distribution in a polar covalent bond? Okay, so electronegativity, let's just go back here and take a look at what that word means again, okay? Because it's a kind of a big fancy word here. So electronegativity is, if we can find where the term, here we go. Or maybe it's not mentioned there. Where do we find it? Okay, well, I don't know exactly where in the notes it is said, but the word electronegativity means how badly an atom wants electrons, okay? So the value that we have for electronegativity is if something has a very high electronegativity value, then it really, really, really wants electrons. It will pull those electrons towards it. And if something has a very small electronegativity value, that means that it doesn't want electrons. It will kind of push electrons away. So the question here is asking, how do those electronegativity values determine the charge distribution? Basically, it's just saying, how do the values for electronegativity determine where the charge is mostly going to be in a polar covalent bond? And the atom that has the higher electronegativity value will tend to be more negative or slightly more negative in a polar bond. And the atom that has a smaller electronegativity value will tend to be more positive in a polar covalent bond because it's going to push those electrons away. So basically, we're going to give an answer that says something like this. The electronegativity values will determine which atom is slightly more negative and which atom is slightly more positive. And we can even say larger value equals negative and smaller value equals positive. Okay? I know that formatting isn't great there, but trying to save on some space. Maybe even make our font a bit smaller. Let's maybe go to size 18. There we go. Okay. Number 3, what happens when polar molecules are between oppositely charged metal plates? All right, so there's a picture here that shows this, but because polar molecules essentially have slight charges on them, when you put them between two magnetic plates, the molecules will essentially arrange themselves in a way that the slightly negative end will be towards the positive plate and the slightly positive end will be towards the negative plate. So they kind of tend to line up. Okay? So let's say, let's change our font size here to 18. So let's say the polar molecules will tend to line themselves up in accordance with the charges of the magnetic plates. All right. Number 4, not every molecule with polar bonds is polar. Explain this statement. Use CCl4 as an example. All right, so we're going to be doing some drawing here. Okay, there's the reason why I have it set up this way right now. So you might be wondering, like, why are you sitting in your awkward stool and your giant tripod here? Well, this is why. So we're going to draw out CCl4, and we're going to take a look at why this molecule is not polar, even though it does have polar bonds. So let's first draw it. Okay, so we have CCl4. So count total number of valence electrons we have is carbon, which is 4. And then the chlorines, and there are 4 of them, and each one has 7 valence electrons. So 7, 7, 7, and 7. Okay, so if we take 7 times 4 here, that is 28 valence electrons, plus the 4 from the carbon. This gives us a total of 32 valence electrons. So we draw this out. Our carbon will be in the middle. We'll put our 4 chlorines around the carbon, connect them all up with single bonds. So of our 32, we've used 2, 4, 6, 8 electrons, which means we have 24 electrons left. So now we'll distribute these as lone pairs. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So we have 0 electrons left. Here is our drawing. Let's double check the octet rule just to make sure that it's drawn correctly. Carbon, we have 2, 4, 6, 8 electrons on. And the chlorines, we have 2, 4, 6, 8 electrons. All right, so this is drawn correctly. Here's our drawing. Now, let's check the negativity, the electronegativity values for carbon and chlorine. So we're going to go back to our notes and use the chart that we are given with the values. Okay, so let's again zoom in here so we can see. So carbon has a value of 2.5 and chlorine is 3.0. Okay, so we're going to write that on our sheet. So carbon is 2.5, chlorine is 3.0. Okay, so this is 2.5, this is 3.0, and all of these, of course, are 3.0. So if we subtract these two, we get a difference of 0.5. So on our, again, chart of values in this difference chart in our notes, 0.5 would fall into the moderately polar covalent range. However, this molecule is not going to be polar, okay, and here's why. Polarity is primarily when you have an imbalance of charge. So if we look at this, although these chlorines are more negative, okay, they're more electronegative, they're going to tend to want to pull electrons away from the carbon. The main difference is that there are 4 chlorines and all of them are going to be pulling electrons away from the carbon, all in balanced and opposite directions, which basically means all of these chlorines are going to balance each other out. So even though they're all pulling away from the carbon, they're all essentially also pulling from each other, which ultimately will then basically make it so that none of them are going to pull the electrons closer to itself. So they're kind of balancing each other out, which means that on the overall molecule, there will be no part where there is a slightly negative charge or slightly positive charge. Everything will be distributed evenly because it's balanced, okay? So therefore, it is not polar overall. We have polar bonds, but the overall molecule is not polar, all right? So we're going to write that in our question, and we'll look at how we're going to word this properly, but let's go back down to our question. Let's zoom back out so you can actually see it. That would be good. Okay, so we're going to say something along the lines of this. Although the carbon and chlorine bonds are polar, because there are 4 chlorines that are all pulling electrons away from the carbon, the overall charge distribution is balanced and the molecule is not polar, okay? So the charges are kind of distributed evenly, they're balanced out, so it's not polar. All right, last question here, number 5. It says, draw the electron dot structure for each molecule and identify polar covalent bonds by assigning slightly positive and slightly negative symbols to the appropriate atoms. All right, so we're going to have to draw some molecules out. I'm going to draw these out faster than I usually would, so I'm not going to go through the whole like count electrons and blah, blah, blah. I'm just going to draw these out just for the sake of time. If you're still struggling with drawing molecules by this point, I would go recommend rewatching the videos on how to do that or go looking at some other practice here. But either way, so for letter A, we have H, O, O, H. For letter B, we have BrCl. For letter C, we have HBr. And for letter D, we have H2O. Okay, so again, I'm just going to draw these out real quick. I'm not going to go through the whole process of how do we do it. So we'll have H, O, O, H, and it's going to look something like this. Okay, again, if you're like, how did you get that? Go watch some of the other videos of how to draw molecules, but right now I'm just going to save some time. So, all right, here is our BrCl. Here is our HBr. And our H2O is going to look like this. Okay, so here are our molecules. Let's go check values for these elements. So for hydrogen, we'll check the value of what its electronegativity is. Oxygen, same thing. We'll check bromine. We'll check chlorine. Then we'll have these two down here. And then same thing. Okay, so, and oxygen. All right, so let's go check some values real quick. We're going to need to use our notes and look at our chart. So let's go back up to here. Let's zoom in so we can read it better. Okay, so hydrogen, hydrogen's over here. So hydrogen has a value of 2.1. Okay, so we're going to write 2.1 for our hydrogens. So 2.1, this is 2.1, 2.1, and 2.1. Okay. Let's take a look at oxygen. Oxygen is 3.5. All right, so let's go write 3.5 on our sheet here. So 3.5 for the oxygen, 3.5 for the oxygen. And then we'll take a look at bromine and chlorine. So bromine is, and make sure you have the right screen up. Bromine is 2.8 and chlorine is 3.0. All right, so 2.8 and 3.0. So 2.8, 2.8, 3.0. Okay, so now let's find our difference for all these. So difference, 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 difference. All right, so 2.1, 3.5, that's a difference of 1.4. This is a difference of 0.2. This is a difference of 0.7, and this is a difference of 1.4. Okay, so looking at this then, the oxygen is going to be slightly negative. So this will be slightly negative. This will be slightly negative. The hydrogens will be slightly positive and slightly positive. For the bromine and the chlorine, difference of 0.2 falls in the nonpolar range. So this is going to be nonpolar. Okay, so there will be no slightly negative and positives. For HBr, 0.7, that falls into the moderately polar. So this is going to be slightly negative because it has a larger electronegativity value. This will be slightly positive because it has a less electronegativity value. Okay, that's how I got these ones up here. Again, oxygen is more electronegative, so we have slightly negatives here and slightly positives. And then H2O, we have a difference of 1.4. So this is going to be slightly positive and slightly positive on the hydrogens because the electrons are going to get pulled into the oxygen. And this will be slightly negative because, of course, it's pulling those electrons in. Okay, so of our molecules here, again, the question, I believe, is asking us to determine or draw the structures, which we've just done, and then identify polar covalent bonds by signing symbols. Okay, so we've done so. Again, we'll take a look at our answers here one more time just to make sure that we have these drawings correctly. But here are our drawings, and we've put our symbols to indicate which things are slightly negative, slightly positive, with, of course, letter B being nonpolar, so there's no symbols there. But yeah, and again, we can have our arrow there to show. Okay, so that is the last question here for number 5. Hopefully, again, that helps you understand polarity a bit better. If you have any questions, though, again, always feel free to email me, reach out, we can chat in class, or maybe do a Google Meet and just do a little bit of tutoring or practice. All right, guys, that's it for this one. Thanks for watching, and I'll see you in the next one. Bye.